Last time, I did not completely finish talking about the autonomic system. And I said, I think, as I wrapped things up, you might not want to submit part 4 just yet because I haven't quite finished all of that. I think some people did submit part 4, and that's fine. I said that because I didn't get a chance to go over stuff here in class, but anything I'm going to go over in class actually is available through other sources, through the reading and the online presentation stuff I put in there. So, I usually just have to review to be sure I know what I covered in class. Did I talk about? I remember drawing up on the board 2 neurons, central nervous system, ganglion, had a heart as a target organ, and I wrote acetylcholines released from both preganglionic fibers, and then acetylcholines released from the parasympathetic and postganglionic fiber, and the norepinephrine's released from the postganglionic sympathetic fiber, right? Okay. What receptor does acetylcholine bind to at the ganglionic neuron? When the preganglionic fiber releases acetylcholine, what's the receptor on the ganglionic neuron, on the target? Right, nicotine. And then at the target organ, what does acetylcholine bind to when it's released from the postganglionic parasympathetic fiber? Muscarinic. And what does norepinephrine bind to? What do we call the norepinephrine? Right, the adrenergic receptors, which are classified as either what or what?
Alpha or beta.
Right. Okay. Specific target organs have specifically an alpha or a beta receptor, but for the most part, we'll just treat them all as one, unless something comes up to say specifically where one is found. Is that where we finished?
Yeah.
Okay. So, actually, let me back up for a second. So the beginning of the chapter is just laying out sympathetic versus parasympathetic, all of these connections, which I started talking about back last week, and I finished up on Tuesday. And then this goes into a little bit more detail about what the connections actually look like, but for the most part, I just deal with everything as basically being synapse. Granted, a neuromuscular junction, which is not autonomic, that's somatic, is sort of a classic synapse. The connections that we see in the autonomic system don't quite look like that, and some sources will not call them synapses, but for our purposes, they are. An example of controlling pupillary size. And then sort of moving on from the layout of, or not the layout, but the example of the pupillary size thing. This is a bit more anatomically correct as to the players in the pupillary light reflexes. That's covered at the end of the previous section of the chapter. And it goes into some things that are important in the central nervous system. I'm actually not going to talk about this too much here, but I do want to point out that the hypothalamus is really important in autonomic function because when we get to the endocrine system, it's also very important there. The hypothalamus is sort of the master control center for homeostatic mechanisms, which it can do either through autonomic or endocrine control. So, and a few other things that play a role. I wanted to spend a little bit of time talking about drugs that have an effect on the autonomic system. Again, this is covered in the online presentation also. Basically, drugs can be classified whether they affect the sympathetic or the parasympathetic side of things. And under the sympathetic side, sort of broad classification is basically just positive or negative effects on the system. So sympathomimetic drugs are drugs that mimic the sympathetic system. So they act the same as norepinephrine, essentially. And a classic example of that is drugs that cause pupillary dilation. If you go to the optometrists and have your eyes checked and they dilate your pupils, these days they actually don't use a sympathomimetic drug because the risk of it getting into your system and causing other sympathetic reactions is problematic. So nowadays, this isn't really what's done. But originally, if you wanted to dilate pupils, you used a sympathomimetic drug. The sort of first and foremost example of that is a drug called atropine. Atropine is an extract from a genus or family of plants. I can't remember what level it all fits together. But they're all known for the fact that they produce this particular drug. One that's worth talking about, just for historical reasons, is called belladonna. And it's called belladonna because it used to be used cosmetically. Causing pupils to dilate makes the eye appear larger. Nowadays, people don't do this for the sake of cosmetics. Instead, eye makeup, lashes, shadow, liner, all those sorts of things will make the eye appear larger than it normally is, or than it actually is, just by accentuating it. But it used to be that dilating the pupils was the way to go about that. What does belladonna mean? And I've been, it's been commented on that I'm not pronouncing things with the best Italian to it, but does anybody know what belladonna means? Anybody?
Can you break it down?
Beautiful something.
Beautiful something, right? Bella means beautiful. Donna, anybody know what Donna means?
Eyes. Eyes.
Nope. Anybody seen The Godfather?
Yeah.
What did they call The Godfather? Anybody know?
The Don.
The Don. Okay. That's the male version of it. Donna is female. So what do you think Don was referring to?
Is it a boss?
Well, in the mafia, the Don's the boss because he's in charge. But Don is just referring to the man. And so Donna is just woman.
Beautiful.
Right. So belladonna just means beautiful woman or beautiful. Hence the name. And a few drops of an extract from belladonna would make the eyes dilate, and it would be cosmetic. The plant belladonna is either also known as or very closely related to another plant in that same family called deadly nightshade. Now, you're probably not likely to try to put drops in your eyes extracted from a plant called deadly nightshade, hopefully. But really, it's the exact same stuff, atropine. So used cosmetically to cause pupillary dilation, it can also be used to cause death. What about a sympathomimetic drug is going to cause death? What would the sympathetic system do that might lead to death?
Harder.
Hmm?
Harder.
Right. primarily, you can play with cardiovascular function. So you give somebody a really strong dose of atropine, it'll cause the heart to race and probably go into fibrillations, and they'll die. Or I suppose blood pressure could go way up. This is less likely to be the cause, but a blood vessel could rupture somewhere and cause problems. Okay. So that's an example of sympathomimetic drugs. There are other ones that aren't quite as interesting stories to tell, but they belong to that group. And then sympatholytic drugs are just the opposite. They, instead of mimicking the sympathetic system, they break the sympathetic system, which is essentially what lytic is referring to. So they will block norepinephrine binding to its receptor or something like that. The best known type of drug that falls into this category is just referred to as a beta blocker. I think I probably mentioned that last time when I was talking about alpha and beta receptors. That drug, beta blockers, just block the beta receptors. And they're usually used for cardiac issues, whether it's high blood pressure or heart issues, to slow down the heart rate and dilate most blood vessels, keep the cardiovascular system sort of at rest. It's stopping the sympathetic side of things, and it's sort of forcing a parasympathetic tone, forcing the body to act like the parasympathetic system is doing its job. And, oh, that's interesting. Okay. That whole belladonna thing I was just telling you about in sympathymimetic drugs in the book is actually here, which makes me think that I was completely wrong about that, what I was just telling you. I could swear that was atropine. Okay, let's not get bogged down with that. Just the concept of sympathomimetic and sympatholytic drugs, I covered that. Exactly where the atropine drugs fall in the group, I'm obviously confused about that today. I could really swear that atropine. All right, looks like I might have messed up in writing this part of the book, but I'll have to double check that. No, here actually in the table that's going over all this stuff for atropine, it says anticholinergic or muscarinic antagonist. So, all right, we'll just figure that I'm confused today. But sorry. The good thing about that is that whole story about belladonna and deadly nightshade isn't crucial. It's not. I was using it as example, and it might seem like I've completely screwed everything up, but really sympathomimetic drugs and what's that called? Anticholinergic drugs are kind of very similar, either activating the sympathetic system or blocking the parasympathetic system. And so atropine, in the sense of deadly nightshade, can still have the same effect. Instead of speeding the heart rate up, it's blocking the parasympathetic system's ability to slow the heart rate down, and it's still going to result in the same sort of thing. So, yeah.
You said the sympathomimetic is similar to the cholinergic.
So sympathomimetic means to mimic the sympathetic system. Okay, and then here, not that you can read on the screen, but the bottom row of this table here about the drugs lists atropine, which I was talking about, thinking was a sympathomimetic drug, is an anticholinergic drug, which means it blocks acetylcholine binding to the muscarinic receptor. So if we activate the adrenergic receptors or block the muscarinic receptors, it's the same effect, either increasing sympathetic or decreasing parasympathetic. ultimately they're the same.
So it's anti-cholinergic instead of the regular cholinergic.
So when I started talking about it mistakenly, I was talking about it in terms of sympathetic system activity, but really an anticholinergic drug like atropine is blocking the parasympathetic system at the target organ. So last week I drew a picture. I'm not going to draw the whole thing, but I had two synapses coming on the heart like this, and norepinephrine is released from the sympathetic side, and acetylcholine is released from the parasympathetic side. Norepinephrine binds to alpha or beta receptors. Acetylcholine binds to muscarinic receptors. Okay, that's basically what I had on the board. Mistakenly talking about atropine, I was putting it as something that activates this, which would increase norepinephrine activity. Looking at the book now, having it in front of me, seeing my mistake, it actually decreases acetylcholine. It's anticholinergic. Okay, so blocking this side would effectively be the same as activating this side. Okay. Everybody get that?
It decreases the CO2.
Right, anticholinergic means to decrease acetylcholine, which is effectively the same as increasing norepinephrine, which is what a sympathymimetic drug would do. We're talking about it mistakenly. Okay. Okay. Oh, okay. At the top of the table here, it's talking about nicotine. Nicotinic receptors are found on the ganglion cells of both sides of the autonomic system. So nicotine is going to activate sympathetic and the parasympathetic side at the same time. For most you can't void bladder when the sphincter's closed, so it kind of cancels out. But nicotine does have the effect, has a couple of effects that are important for cardiovascular system because of some exceptions to this simple setup, like with the bladder I just described. Now with the heart, cardiac muscle, which we'll get to learning more about in a couple of few weeks, whatever, when we get to the heart, is intrinsically active. When you learned about skeletal muscles, you learned about how the nervous system has to tell the muscle to contract. Cardiac muscle contracts on its own. You can actually remove the heart from the body and keep it active in a physiological container. In fact, when we get to looking at the heart, I'll show you that. It's a great way to keep hearts alive when they're transported for transplant. So the classic idea of transporting a heart is a little red igloo cooler where the heart's just on ice and there's a limited amount of time to get it to the recipient. But somebody invented something a couple of years ago where the heart's kept alive by having solutions attached to it and it keeps beating within this box. And that's because cardiac muscle is intrinsically active. You can remove it from everything else and it'll still beat. And so the sympathetic and parasympathetic input to the heart isn't telling it to beat. It's telling it to beat faster or slower. And if both sides of this are arriving at the same time, the heart, which is beating on its own, is getting conflicting information about what to do. And so it will generate arrhythmias, that sort of thing. It'll try to beat too fast and too slow at the same time. It just loses its rhythm. Blood vessels are a little bit different. we usually think of the sympathetic side as causing an increase in blood pressure. We don't think of the parasympathetic side on the other, the parasympathetic division on the other side causing a decrease, because blood vessels generally don't get parasympathetic input. Some do, but not all of them. Ones that we do have to actively dilate will get parasympathetic input, but your average blood vessel is usually slightly constricted normally. That's what's called sympathetic tone. And so we can just make it constrict a little bit more when we want to, and then stop that constriction, and it goes back to its resting diameter. That's all controlled by the sympathetic system, except for a few exceptions where the parasympathetic system plays a role. And so if you're activating both sides equally for blood pressure, since there really isn't a parasympathetic input to systemic blood pressure, the sympathetic side's in charge, and nicotine will just increase sympathetic activity, causing a rise in blood pressure, because there's no parasympathetic trade-off there. And so for the cardiovascular system, nicotine will actually cause an increase in blood pressure just because there's no parasympathetic input to blood pressure, and arrhythmias in the heart because cardiac muscle works on its own and the input just confuses it, to put it simply. So a lot of that is explained in this section here, and better than I might have done it today, so please go to this. But the basic idea that I was talking about today, within the sympathetic system, we have sympathomimetic drugs and sympatholytic drugs, which either activate or deactivate the sympathetic side. That's pretty straightforward, I think. The example I used, unfortunately, was mistaken. I forgot where I was supposed to go with this. And on the parasympathetic side, technically we could say the same thing, but we don't really have too many, or we don't break down parasympathetic drugs quite the same way. In the parasympathetic system, anticholinergic drugs are the ones that are most important, which will stop the parasympathetic system from doing what it's supposed to do.
So the anticholinergic is the same as the sympathomimetic, or it's similar?
In the end, it'll have similar effects, but a sympathomimetic drug and an anticholinergic drug operate in different exact ways. So a sympathomimetic drug will increase this activity, and anticholinergic will block that.
Oh, okay.
So by removing parasympathetic input, you're effectively letting the sympathetic system become more active.
So it's
Or you can just make the sympathetic.
just a different route.
Right.
Same.
And sometimes you don't want to use sympathomimetic drugs because they might have side effects like increasing heart rate or something like that. So you'd use an anticholinergic drug instead. Not that this is a pharmaceuticals class, but just the reason why there's two different mechanisms to work with. Okay. So that takes us, oh, that's right. That takes us through the rest of what I wanted to cover in the autonomic system. Just talking a little bit about the drugs. And please go to the reading. I kind of mangled it today, which isn't impossible for me to do. So go into the reading, and I was able to be a little bit more thoughtful when I was reading and making sure that I put things in the right places. But there you have it. Question.
The online content, is that the same as the video content?
So the online content is recordings of me doing lecture material over presentation slides. So, and there's a folder after the reading link. It says, sorry?
That's the YouTube.
No, it's not YouTube. YouTube is me recording this. The online content is me using a presentation software and adding voice to it, explaining each slide, which is basically lecture. I'm doing it a few different ways so that people have different options of what they want to look at. And that the online content I'm talking about is what's in the folder in each week's material. So after the reading, you click on the folder that says online content, and that's where you can see that stuff. It's not a YouTube video. It's okay. So as I was finishing up the autonomic system stuff, I just hit the next button in the book, which took me to the next chapter, which is the neurological exam. That's something I use in AP1. So we're chapter 15 was the autonomic system. This is the first semester I've had to deal with them numbering the chapters this way. The neurological system was, the autonomic system was chapter 15. The next chapter, 16 in the book, we are not doing this semester. It's something I do in AP1. And so we're going on to the next chapter, which is 17, which is the endocrine system. Now, what I want to do today is talk about the signaling molecules involved in the endocrine system. And then Thursday, we'll talk about some specific examples of endocrine function. While I'm thinking of it, because of yesterday's snow day, trying to keep things on track, I sent an email out to everybody in the Monday lab, letting them know that in fact lab was canceled. I also sent a link to a YouTube video, which was me doing what we would have done in lab. I recorded it last semester. What I recorded actually was my night class, which is 3 hours long. And I sent you a link to the second half of that recording. The first hour of that was the lab material, which I would have done in lab yesterday. So you can see that. If any of you in the Monday lab group would like to attend the lab, you're welcome to come to tomorrow's lab. Same place, same time, different day. And you can do that. I'm not going to delay our lab schedule till next week. It'll just throw everything off. And that particular lab I had recorded. I knew I had a decent version of it. Whether you watch it on YouTube or you sat in the room and watched me say it in class, it's not terribly different. But if you would rather be in class and watch and have the opportunity to get some questions or feedback in, you're welcome to come tomorrow. Next week in lab for the Monday group, we'll be doing the blood lab. Wednesday group 2. Also, while I'm thinking about it, Monday lab next week is on Tuesday because of the holiday. And we do not have lecture on Tuesday next week. So I'll probably say that again on Thursday this week and just want to reinforce something. So today, like I said, I want to talk about the signaling molecules that are involved in the endocrine system. And Thursday, I'm going to talk about some examples of endocrine function. Some of those examples of endocrine function are covered in lab also. And I might on Thursday decide to skip a little bit of the presentation in the interest of time because I might have already talked about it in lab. So I'm using this term signaling molecule. And that's just a very general term for molecules that are used to signal things. We're quite familiar with a class of signaling molecule already. It's come up several times, which is neurotransmitters. So let me just quickly just write this up on the board. And I'm going to write some under this. So if you're putting this in your notes, leave a little bit of space or hold off to write anything until I And then in this chapter, we're going to be talking about hormones. Now, there are some situations where the exact same molecule falls under both of these classifications. So really calling a signaling molecule a neurotransmitter or hormone is really just a matter of how we define these things. Where do we see neurotransmitters? Right. Neurotransmitters diffuse across synaptic clefts, which is just a wordy way of saying what you just said. But there's a reason why I'm being wordy. Synaptic cleft is the very, very short distance between the end of an axon and the target's cell. And the neurotransmitter diffuses across that very short distance. Hormones are often defined in the same sort of way based on where we see them diffusing. Where are hormones found? Anybody know? Yeah, they go through the blood. So they so for neurotransmitters, how far are they traveling?
Not far.
A very, very short distance. Anybody have any idea how far that distance actually is? Right, it's probably measured somewhere in the nanometer range. Whoops. No. And how far do hormones travel?
Far.
All over.
From
All over the body.
here to New York City?
All over your body.
Yes, they can travel throughout the body. Whoops. Which may be maybe as far as 1 to 2 meters. A great go-to example of a hormone that most everybody's familiar with and will satisfy a lot of this kind of definition is insulin. Insulin is released from the pancreas and travels throughout the body. Now, I said maybe as far as 1 to 2 meters, but that's actually not likely to be quite 2 meters in length. Something that's going to travel 2 meters would have to travel from the top of somebody's head to their toe or something like that. So maybe just 1 meter is a better example. But so if we start at the pancreas here, cells in the skin of your big toe will get that signal. So that might be 1 meter or so away from the pancreas. Now, what do neurotransmitters bind to on the target? Right. And so we call those neurotransmitter receptors. And what do hormones bind to?
Target cell.
But what on the target cell do they bind to?
Gland.
No, the glands are what's releasing them. What do signaling molecules bind to? We got one type already up here on the board. That's a big clue to what the answer to my question was.
Hormone receptor.
Right. They bind to a receptor. Okay. When a hormone binds to its receptor, we call that a hormone receptor. When a neurotransmitter binds to its receptor, we call that a neurotransmitter receptor. More accurately, we just call the receptor whatever binds to it. So adrenergic receptor, insulin receptor, acetylcholine receptor, et cetera, et cetera. It's just a matter of what's actually binding to them. The point I'm making here really is that signaling molecules all bind to receptors. So neurotransmitters bind to their receptors, hormones bind to their receptors. Now I want to mention a little added thing about hormones that's lost in how I defined it here, which is they diffuse through the bloodstream usually, but sometimes we can have paracrine or autocrine effects. Okay. Now, endocrine, paracrine, and autocrine all have the same root to their word. Does anybody know what crine means? C-R-I-N-E?
Hormone?
Nope. I actually set this up when we were talking about the autonomic case study. People, I don't remember if, yeah, it must have happened. When I ask about which system the sweat glands are part of, people often will erroneously say the endocrine system. And so I take that as an example, a chance to define endocrine. So, do you remember in lab that coming up, somebody saying endocrine? We talked about the word endocrine a bit.
You said skin?
That's what we talked about in class. What I'm getting at is I took that opportunity when somebody incorrectly said endocrine to define what endocrine means. That come up in your lab? You remember that?
Inside.
Yeah, so the endo means inside, and I also said crine means what?
Where?
Secrete.
So you secrete inside or you secrete outside. So endocrine means secrete inside. Paracrine is talking about a special type of secretion. Autocrine is a special type of secretion. Okay, so crine just means secrete. Any idea what either paracrine or autocrine would mean based on the word?
Parasympathetic is for paracrine.
No, we're in the endocrine system. We're out of the autonomic system.
Auto means cell.
Right, auto means cell. I opened up, anybody could define either of these because I figured autocrine would be the most obvious. So autocrine really means self-secrete, which is a horrible definition. But a cell secretes a hormone, and that hormone binds to its receptor that's on that very cell. Okay, so let's say, I've touched the rubber. Let's say we have a cell here, and it's got secretory vesicles, and it's secreting something outside the cell. But some of those things go back and bind to a receptor on the cell. Okay, that's autocrine. It's a feedback mechanism. It might be that the amount of hormone that's released from that cell, once it gets to a certain concentration, there's enough of it there that it'll bind to that receptor until the cell stops secreting. That's a negative feedback signal. Actually, the best example I have of that, which is in the digestive system, is the exact opposite. When a cell in the lining of the stomach releases its hormone, some of that hormone binds directly to that cell, which tells that cell to make more hormone, release more hormone. Just increases the activity. But yeah, autocrine means self-secreting or activating itself. Any idea what para as a prefix means in a word?
Not two.
No? Remember why parasympathetic was called that?
Opposite.
Nope. It's around the sympathetic side. Okay. It's a little bit above, a little bit below. It surrounds it. So paracrine means to secrete around. Roughly. So going back to this picture, there might be a neighboring cell that gets that signal and it's activated. The hormone has not traveled through the bloodstream, it's just going to another cell in that same tissue. That's paracrine. So this is autocrine, this is paracrine. And then some of that will get into the bloodstream and travel along and get out and have an effect elsewhere. That's endocrine. So these three terms, endocrine, paracrine, and autocrine, really just are talking about how far away the target is. If the target is the cell that's secreting the hormone itself, that's an autocrine signal. If it's a neighboring cell, that's paracrine. And if it's something that has to be reached by going through the bloodstream, that's endocrine. Some sources will want to treat autocrine and paracrine as different things, but really it's all the same. And in the example I've drawn here, this cell is secreting the hormone. We can't say this cell is three different things. It's one cell. It's just what it secretes has three different effects. One on itself, one on its neighbor, and one on a far target. So those sources that try to separate autocrine and paracrine out from endocrine because it's not going through the bloodstream are really just ignoring some effects that hormones can have in local areas. The cell I was mentioning before that releases a signal that activates itself in the digestive system is a perfectly good example of what I'm talking about here. It releases a signal that tells itself to make more hormone. It also tells its neighbors to make more of what they make, which is stomach acid or digestive enzymes. And it can travel through the bloodstream and tell tissues elsewhere, like on other parts of the stomach, to do the same thing. So it has actually all three functions in it. We can't really separate it out. But they're obviously different from neurotransmitters because it's not happening at a synapse. Now there are auto effects at synapses. Sometimes the receptor will be on the releasing cell as well as the target cell at the synapse, but still it's within the synaptic cleft, which makes it a neurotransmitter. But if we're not in a synapse, regardless of exactly how far the molecule actually travels, all those other things we're going to consider hormones. Sometimes the exact same molecule can be called a neurotransmitter or a hormone, depending on how it's used. Serotonin, for example, is very well known as a neurotransmitter. It's tied to sleep and wakefulness. It's the target of antidepressant medicines like Prozac and Zoloft and those sorts of things because of what it does at synapses. But it's also released by a whole bunch of cells throughout the body as a hormone. We actually won't deal with serotonin as a hormone too much in this class, but it is an example of a molecule that's used in both ways. So, when you're wondering whether something is a neurotransmitter or hormone, please pay attention to how the signal gets to the target. If it's going through a synaptic cleft, we call it a neurotransmitter. If it's going through the bloodstream or one of these other versions that is under the same group, then we call it a hormone. Again, some sources might call signaling molecules that do these things something different, like a paracrine agent or an autocrine agent, but really it's often just a hormone having other effects. Okay. In this first section in the chapter, it sort of compares neural and endocrine signaling, and compares the nervous system and the endocrine system in that table that is at the bottom of the screen right now. And then it just sort of goes over the major instructions of the endocrine system. I'm actually going to cover that in lab, because in lab we're going to be looking at specific organs, so I won't deal with that here. And then after where it lists the different glands that we consider endocrine organs, it has this section that says other types of chemical signaling. And this is where it defines autocrine and paracrine. But really, those are hormones also just having an effect closer than having to move through the bloodstream. And in fact, not that you can read it on the screen, but it says, in endocrine signaling hormones secreted into the extracellular fluid. Okay, I don't quite want to go there, but it's laying out the different places where hormones can go. And in this section, they don't quite draw the connection that sometimes the same cell releasing a particular chemical can have autocrine, paracrine, or endocrine effects, but it's in fact true. And we're going to meet that cell when we get to the digestive system later in the chapter. I mean, later in the semester. This next section, which is just titled hormones, introduces a number of different hormones. I want to talk about them in a slightly different way than the chapter here introduces them, but then the chapter gets around to talking about them the same way that I'm going to. And that is what type of molecules they are. And again, we're talking about hormones here. We're not going to talk about neurotransmitters. We've done that in the autonomic system and then back in AP1. So from here on out, everything we're talking about, we mean hormones. Essentially, hormones should fall into two major groups based on what type of molecule they are. They are either lipid soluble or water soluble. And considering these two things, we want to keep three different things in mind. Actually, let me write this on the board slightly differently. I just need a little column over here to put some stuff. So. Let me think here for a second. Okay. So we want to consider the molecule, how it's transported, and the receptor. So for the molecule part of this, everything I need to say about the type of molecule is really in the name. Lipid-soluble molecules are lipid-soluble. Water-soluble molecules are water-soluble. But let me give you some examples of lipids. The biggest one are steroids, which are derived from cholesterol. And the other big one that we're going to deal with are thyroid hormones. Which are T3 and T4. And then water-soluble molecules are amino acid derived or peptide or protein. And really those three terms aren't terribly different from each other. What are proteins made of?
Amino acids.
Amino acids, right. Okay. So we could say a protein is amino acid derived, although that's not really what the term means. And then what is a peptide? A chain of what?
Amino acid and
Right, so peptide's a chain of amino acids. Okay. How's that different from a protein? As we've defined it so far, it's not. Right. The real difference between peptide and protein is length. Peptides are short, proteins are long, but they are still both just chains of amino acids. Okay. Now, to say something is amino acid derived really doesn't mean that it's amino acid chained together. Those are molecules that are made by enzymes using amino acids as the raw material. Okay. We've actually already met an amino acid derived water soluble hormone, which is epinephrine. I talked about norepinephrine as a neurotransmitter for postganglionic sympathetic fibers. And when I was talking about norepinephrine, I introduced epinephrine as a word, right? Talked about. We also call norepinephrine noradrenaline. Epinephrine is also adrenaline because it's just a Greek or a Latin version of the name for molecules that come from the adrenal gland. Remember that last time?
Yeah.
Okay. The amino acid that those are derived from is called tyrosine. So there's an enzyme that modifies tyrosine into another amino acid, which happens to be called L-DOPA. And then there's an enzyme that modifies L-DOPA into a molecule called dopamine, which is usually considered a neurotransmitter in this course. But then another enzyme will change dopamine into norepinephrine, and then another enzyme will change norepinephrine into epinephrine. Okay, so there's just a series of enzymes that modify this amino acid called tyrosine, and depending on how many steps we go through, we either get dopamine or norepinephrine or epinephrine. Okay. Cells that release dopamine just don't have the enzymes to make norepinephrine or epinephrine. Cells that release norepinephrine just don't have the enzyme to make epinephrine. And then the ones that make epinephrine have all of the enzymes. But that's really kind of an example of amino acid derived. Another amino acid derived example is melatonin. Anybody ever heard of melatonin?
Mm-hmm.
Where does that come from? That's melanin. I gotcha. They're very close because they both have a similar property, which is why melanin is called melanin.
Isn't melatonin what gets you like sleepy?
Yeah.
It's with any food.
Yeah, I think so. It's you can tell you can use the source of.
Okay, so
We naturally make it.
yes, we naturally make melatonin. You can take a melatonin supplement. It's not found in food because it's amino acid derived. The amino acids derived from is found in food. It doesn't exactly make us sleepy. It's actually the signal in your body to let you know when it's nighttime. Okay. When the sun goes down, the pineal gland makes melatonin, releases it throughout your body, and your body knows that it's nighttime. Some people can train themselves to stay awake at night and sleep during the day, so it doesn't make them sleepy. It's just a signal, and their body's trained to recognize that as a signal to be awake. But the connection you just made to food is actually a misconception a lot of people have. Usually you hear a lot about it around Thanksgiving. You'll hear people talk about tryptophan and turkey and making you fall asleep and going into a coma, et cetera, et cetera. That's not true. On Thanksgiving, when you fall asleep because you just ate a lot of food. Okay? Tryptophan is in fact the precursor for melatonin. It's in fact also the precursor for serotonin. And it is related to sleep and that sort of thing, but the amount of tryptophan you get in your food does not directly relate to how much you sleep. Okay. There's actually a very nice Mythbusters episode where they address this. They have, if you're familiar with Mythbusters, there's Adam, Jamie, who are the cool Mythbusters people. And then there are these three like lesser Mythbusters, whose names escape me right now. But they were in charge of that part of the episode, and they we're testing the ability of people to be active following eating a Thanksgiving meal and comparing that to other food sources. It's kind of funny, the way that they tested this was they played whack-a-mole. That was their test-dependent variable for how alert somebody was, how many moles they could whack in a given amount of time. So they did a baseline to see how much the two guys in that group could play whack-a-mole, and then gave them a melatonin pill, or gave them a Thanksgiving meal, or gave them a non-Thanksgiving meal with the same number of calories as one would eat at Thanksgiving, or eat a Thanksgiving type meal, but with the amount of calories that would be eaten in a regular meal. Okay. What they found was melatonin did in fact change their whack-a-mole abilities, not as much as the food did, but the only thing that affected their ability to play whack-a-mole well was how many calories they took in. Okay. So you eat a big meal, whether it's turkey and stuffing or whatever else they were serving, I can't remember. It's the calorie count that translates to being sleepy. Eating turkey in a normal caloric level meal didn't have any effect. So it's not about the turkey, it's not about the tryptophan, it's just about the calories that are taken in and how active your digestive system is. So, but that's tryptophan. Makes serotonin, which is generally considered a neurotransmitter for this course, and melatonin, which is a hormone. Now, with a few exceptions, pretty much everything we're going to talk about are protein hormones. Okay, they're the most common hormone that we're going to deal with. But there are a few examples of amino acid derived or peptide. And then for the lipid soluble ones, they're found in very specific places. Where do you think the thyroid hormones are found?
Thyroid.
In the thyroid, right. Okay. And then steroids are found largely in the adrenal cortex, and then also they're associated with the reproductive glands. Okay. Now I put here that steroids are made from cholesterol. If you look at a picture of what a steroid looks like, which I don't think you're going to be able to see terribly well on the screen here. Maybe you can kind of make it out, but you'll see it in the book. This basic structure, a six-sided ring, a six-sided ring, a six-sided ring, and a five-sided ring, that's what cholesterol looks like. Steroids are made from cholesterol because we get cholesterol in our diet, and then we just modify the cholesterol molecule to make steroid hormones. In the reproductive system chapter, we'll be looking a little bit more directly at the pathway to making steroid hormones. But here, just steroids have a particular structure because they're made from cholesterol, and cholesterol is a lipid. And then the thyroid hormones are kind of weird. And this is, I want to point this out because of what the book's doing here. The book with the table that you can kind of see on the screen there is talking about where different types of hormones come from in the sense of amino acid derived, peptide, protein, or steroid derived, without thinking about whether they're lipid soluble or water soluble. And because of the way they do this, they put thyroid hormones in with the amino acid derived, which is not incorrect. Thyroid hormones are made from an amino acid also. They just don't end up the same way that other amino acids end up. They're made actually from tyrosine also. Okay? They're not at all related to dopamine, norepinephrine, or epinephrine. They just happen to come from the same basic stuff. Tyrosine, as an amino acid, has a six-sided ring structure in it, which is the important chemical structure that's needed. And for epinephrine and norepinephrine and dopamine, this ring structure is part of a bigger molecule. For the thyroid hormones, they're usually drawn as two six-sided rings like this, because two tyrosine molecules are used. The ring structures are taken out of tyrosine and linked together, and the rest of the amino acid is no longer present. What is present, however, is and I'm not necessarily drawing these in exactly the right place in this picture, but I think sticking off of the ring structures here are iodine atoms. We're going to only and ever, except for what I'm about to say, refer to the thyroid hormones as T3 and T4. Just much easier to do that. But the full name for T3 is triiodothyronine. The tri in that means 3. Iodo is referring to iodine, and then thyronine is just a chemical structure. So we call it T3 because it has 3 of these iodine atoms in it. Okay. T4 is not necessarily 4 iodine atoms. It's just very closely related to T3, and so it just got numbered T4 like it was a sequential numbering. There's nothing in the full name for T4 that refers to 4 or anything like that. It just happens to be called T4. There is no T1 or T2, just T3 and T4. And the 3 again comes from the particular name of that molecule that has the prefix tri in it. And it needs iodine in it to work properly. Where do you get iodine? Yeah, you get it in your diet usually through the salt that you use. Okay. What is salt? Table salt. Sodium chloride, right. No iodine there, just sodium and chloride is the salt. Iodine is added to sodium chloride so that you get it in your diet. It's iodized salt. If you don't buy your salt from the supermarket or something like that in that form, then you're not getting iodine in your salt. It is entirely possible to get iodine from other sources in your diet, but it's not that common for people to eat enough of whatever sources of iodine there are in their diet to get enough. Okay. So in developed countries, iodized salt was introduced so that everybody gets iodine. Does anybody know what condition that protects you from having iodized salt? Right. What's a goiter?
Like a big swollen gland.
Yeah. On your neck, you'll see this big swollen thing. That's a goiter. What gland is it swelling? Is it,
Thyroid.
yeah, it's the thyroid gland swelling up. If you don't get iodine in your diet, then your thyroid gland can't work properly and it results in swelling, which is this big obvious thing on your neck. And my gestures here suggesting how big it can be are not an exaggeration. They can be really big. Yeah. Yeah, they're lovely. You can correct that problem just by getting iodine in your diet. Okay, and none of you have to worry about goiters because you probably eat iodized salt. There are probably people out there, because this is the land of the free and the home of the stupid, that people are sure that iodized salt is some sort of government conspiracy. Okay? And so there are probably people in America with goiters because they're not getting iodine in their diet, because they don't trust them government people to give them their salt or whatever. But generally speaking, we don't see goiters in America.
How did you get it prior to this?
Sorry?
How did the populations get it prior to?
So I think iodine is found in, I can't remember. I'm always going to say green leafy vegetables for that kind of thing, but I don't know if that's actually where iodine comes from. But yeah, I mean, you can look up them. There are normal dietary sources. It's just that I think the standard American diet or developed country diet doesn't usually include any of those natural sources of iodine, or very many of them. So just it's supplemented and it helps out. But yeah, so if you are thinking that there's a government conspiracy that you should be eating iodized salt, then please do get iodine in your diet from some other way. But in my mind, the people that are thinking that about the government are also the people that are living off of chicken McNuggets or something like that. So they're not getting iodine. Well, that can't be true, because if they're living off of chicken McNuggets, they're getting iodized salt in their McNuggets, for sure. But whatever. Classifying the molecules based on lipid or water soluble. In the book, they're going to make it sound like thyroid hormones fall in with these other types here, and I just wanted to separate them out because thyroid hormones are, by their very nature, lipid soluble. Now, one thing about thyroid hormones, there are actually 3 thyroid hormones. Only 2 of them are referred to as thyroid hormones, and those are T3 and T4. The third hormone that's found in the thyroid is called calcitonin. What do you think calcitonin is responsible for? Something about calcium. Yeah, the name. But yes, it does therefore have a lot to do with bones because that's where we keep calcium in our body. That's actually a protein hormone. Okay. And in lab, when we're looking at the thyroid gland material, I'll explain the difference between those hormones, but because it has something to do with what the tissue looks like. Okay. I'm probably not going to get to talking about the receptors today. I might pick that up on Thursday. But how these are transported is very important. Where, generally speaking, do we think of hormones as traveling? Sorry?
Through the blood, right?
Yes, it sounded like you said butter, and I'm like, what? Yes, they travel through the bloodstream. Okay. What is the blood primarily made of? Well, has a lot of plasma in it, which is pretty much all, I think you said it, Casey, water, right? So water-soluble hormones will be just fine going through the blood. Okay. So these are freely soluble in the plasma. But what about lipid-soluble hormones? Yeah, they're the same class of molecule that we think of as fat, okay, or oils, which do not mix with water, okay? So to be transported through the blood, lipid-soluble hormones need specialized transport molecules. Which are usually proteins, because proteins are just the best suited type of molecule for doing this. Remember when we were looking, those of you that didn't have me for AMP1 can do this, and those of you that did probably forgot by now, but I just did it with my AMP1 classes last week. I did a protein folding exercise. Anybody remember that from the beginning of AMP1? And some of the amino acids and proteins are lipid or hydrophobic, and some are hydrophilic. And so you can surround the lipid-soluble hormones with the hydrophobic amino acids in protein, and then protect all of that from the water surrounding it with the hydrophilic amino acids. The most common transport protein is called albumin. And that's a plasma protein, which we'll meet when we talk about the blood. But it has these little pockets that cholesterol and steroids and those sorts of things can just sort of fit into so that they can travel through the blood without being exposed to the water environment. Okay. Now, I'm not going to have time to completely talk about receptors, but just let me add something here in the last bit to finish what I have on the board here, and then we'll come back and talk about the receptors next time. Lipid-soluble receptors are inside the cell, and water-soluble are on the cell membrane. Now, when we talk about receptors, when we have talked about receptors up to this point, we've been talking mainly about neurotransmitter receptors, and you probably have in your mind a thing on the cell surface is something that a molecule binds to. All of the molecules that we've talked about so far that bind to receptors are water soluble. So their receptors are all on the surface of cells. Neurotransmitter receptors are basically all on the surface of cells. But lipid-soluble molecules, being lipid-soluble, can dissolve straight through the cell membrane because the cell membrane is made of what? Lipids, right. Okay. So they are not stopped by the cell membrane. They get into the cell. Therefore, their receptors are inside the cell. So what I want to start with next time to finish this out is just to compare the two receptor systems, what lipid-soluble receptors for lipid-soluble hormones look like, and then remind you, because you've actually already seen them, what receptors for water-soluble hormones look like. But I just wanted to put that last bit in here just to finish the table out. I might have written a bit more underneath this part, and I'll add that two things next time. Tomorrow, Wednesday lab group, of course, has lab. Anybody from the Monday lab group that would like to sit in on that, please do. I did send you a YouTube video that basically does everything that we did, or does everything that we will do. And then we'll have a lecture on Thursday. Next week, Monday's a holiday, so the Monday lab group meets on Tuesday. We do not have a lecture on Tuesday. And then Wednesday meets like normal. Of course, assuming we don't have any other snow days. So, that's it for today. I'll see everybody tomorrow or Thursday.